So our next topic will be some general comments on bound states. So far we have seen two examples of systems which have bound states. The first one was the particle in a box, where we considered a quantum particle in an infinitely deep potential well, and then we considered how to solve analytically or numerically the quantum particle in a finite potential well. However, it's worthwhile to discuss what happens in general bound state potentials, because we want to develop our intuition about bound states. So, let's consider the time-independent Schrodinger equation. So the time-independent Schrodinger equation has this form. Now, in many cases, because the potential v of x has some complicated form, that you cannot solve this equation exactly. So even if you can solve this exactly, sometimes the exact solution doesn't mean that you actually have physical intuition about the solution. And as physicists, we should value physical intuition over mathematical exactitudes. So let's try to develop our physical intuition about bound states, about one-dimensional bound states. By the way, by bound states, we mean that we are looking at states whose energies are less than the maximum value of the potential, so that those are going to be genuinely bound states. So for such potentials, there will be two regions of the potential. One region would be where the energy would be greater than the potential in that region. So in such regions, the Schrodinger equation will look like this. There'll be a second order differential equation, and where k squared is a positive number, and k squared is related to the kinetic energy, and the kinetic energy in this case is this is k. The kinetic energy in this case will be a positive number, and therefore k will be a real number. So this is one a region. Another region would be where the energy would be less than the potential energy over there. In such a region, the kinetic energy would be negative, and the Schrodinger equation, its form is given by something like k1 squared psi, where k1 is given by 2m v minus e. Now remember that v is greater than e in this region, square root divided by h bar. So these two equations have almost the same form, but notice that k1 squared and k squared are both positive numbers, but there's a sign difference here. In region 1, it is a minus sign. In region 2, there's a plus sign. So, for example, for definiteness, we can take the case where we have a finite potential well. So this is our potential, and our energy is something like this. So over here, the potential has value v equals to v naught, and over here the potential has the value v equals to 0. So in region 2, but that is in this region and this region, the second form of this Schrodinger equation is going to be valid. And in those regions, the solution of the Schrodinger equation will have the form of exponential of plus minus k1 of x, where the sign of this exponent will be determined by the fact that we require the wave function to decay as we go further and further away from the region 1. And that's because we're looking at particles, we're looking for solutions where the particle is constrained to be in this potential. So if we take the sign of this wave function such that it grows exponentially as we go away from the potential, then we would be looking at an unphysical solution. So we have to choose the sign carefully to make sure that we choose the wave function which is exponentially decaying in region 2. So on the other hand, if you look at region 1, then in region 1, we would expect the wave function to be given by a sinusoid. What do I mean by a sinusoid? By sinusoid, I mean either a sine function or a cosine function. That is, it's going to be a sinusoidal function. Now, how are we going to match up these two solutions? Remember that for finite potential wells, we have to match both the first derivative of the wave function as well as the wave function across boundaries. So these are continuity conditions that we have to match across boundaries or wherever the potential changes. So this is a point where there's a boundary. We have to make sure that the wave function and its first derivative matches across these boundary points. So another general observation is that in region 1, region 1, where we have our Schrodinger wave equation has this form. Because of this minus sign, the curvature of the wave function is such that it concaves towards the x-axis. So what do I mean by that? So suppose that we have a wave function, and as this is our x-axis and this is the wave function. So the wave function will have a form such that because of this minus sign, as we change x, it'll curve towards the x-axis because of this minus sign. So it'll have the form of something like this, or if the wave function is negative, it'll be something like this. Whereas in region 2, where the wave equation has this form, the curvature of the wave function will be such that it'll curve away, it'll concave away from the x-axis. So it'll be something like this, or this. So these are some general comments which we should keep in mind when we try to figure out qualitatively the wave function for a given problem.